Jayce Getz here, speaking about harmonic analysis on certain spherical varieties.
All right, well, thank you very much for the invitation, and annyeonghaseyo and buenos noches, depending on where you are. This is coming from straight from Korea right now. So I'd like to talk, let me just start by, I guess I should say that this is joint work with my NSF postdoc, Spencer Leslie, and my graduate student, Chun-Hsien Su. And Spencer's on the job market this year and he'd be an excellent hire. So there's a plug. So I want to start by a little bit of motivation and necessarily a little brief. Let's start with global field. You're not going to lose a whole much by just taking it to be a number field or even Q. G, a reductive group over F, and X, a G spherical variety. And honestly, for what I'm about to talk about, I'm not sure. I mean, for applications, being spherical seems to be quite important, but and spherical means that it admits an open orbit under a Borel subgroup. Let's just say the G is quasi-split, so there is a Borel subgroup over the base. I'm not sure whether that's actually even necessary for what the conjectures that I'm going to be talking about, but I'm going to assume that it's affine. And it's somewhat important that you allow things that are not smooth. So I'm going to talk first about something called the Poisson summation conjecture. And I call it this because there's too many names associated to it to write down, but I mean to say every time you say it. But so this came out of work of Braverman and Kazhdan, which was sort of rediscovered and refined by Ngo, and also independently discovered in some form by Laurent Lefort, one of the Ford brothers, and it was broadened to the perspective of spherical varieties by Sakellaridis. And then, maybe there's a little bit more that I'm putting in here. And I'm going to talk about this a little bit vaguely, but the idea is as follows. So given this data of a spherical variety and reductive group over F, we should have a Schwartz space, some adelic Schwartz space that is contained in smooth functions on a smooth locus. There should be a Fourier transform from this space to itself. And we may see some generalizations where you have two spaces involved, but you not worry about that at the moment. And that satisfies a GAF twisted equivariance property. And finally, there should be some notion of Poisson summation for this. Okay, and this is for suitable F in the Schwartz space. Okay, so now, I mean, the thing that you should think about, of course, is you think about Poisson summation on the adels itself, or you could think maybe more suggestively of Poisson summation on the space of n by n matrices. And that you think of as a spherical variety because it has an action of GLN cross GLN on either side. And then it being spherical comes down to the Brouillard decomposition. And the idea in those two cases, it's known that Poisson summation implies the functional equations of the standard L functions of Cuss forms. I mean, this goes back to Tate's thesis or even to Riemann with how you prove the functional equation of the Riemann zeta function using Poisson summation. So generalizing that, Braverman and Kazhdan observed that if you had this setup for a particular type of spherical variety, so if this were true, then we would get the analytic properties of quite general Langlands L functions. And then this in turn would imply much of Langlands functoriality. By the converse theorem. So, of course, if you know enough about the twists of an L function by automorphic representations of lower rank, then you deduce that the L function is automorphic, right? So as just sort of an orienting remark on this, if we take F to be something in the Schwartz space, and this is not defined in general, but the way that this thing is supposed to look is something that at some finite bad set of places, it's whatever it is, and outside of some finite set of places, it has some local description. So this is a so-called basic function. And in the case of, say, the matrices, this is the integral points, the characteristic function of the integral points of the matrix, but it's much more complicated in general. So you can, in the case of, say, a reductive monoid, this basic function can be obtained using the Satake correspondence. So there's you have a definition using either Satake correspondence or generalizations that are due to Sakellaridis in his thesis. So Giannis figured out how to compute essentially the what's the right thing to say? It's a generalization of the Castleman-Shalaka formula from the case of a Whittaker function to a general spherical variety. And so you can use that to write down what you expect this basic function to be. And now there's sort of geometrization of this that's due in a special case to Bouthier, Ngo, and Sakellaridis. And now there's a more general version of this that's recently come out that's due to Wang, Sakellaridis and Wang. So, and it's not known in every case, but it's known in many cases. Okay, so that's sort of that's in the generalist, most general setting, that's all we know. We don't, we have some notion of what's supposed to happen at the unramified places. Let's sort of see what in what sort of cases we know something globally. We actually know the Poisson summation formula. So the only case that's completely understood is when X is a vector space. Right? Of course, we understand Poisson summation there, but there are other cases where the global theory is developed, although it's sort of, there's in each of these cases, there's still some questions that remain. So one nice case, which was the first thing that Braverman and Kazhdan worked out, is taking the reductive group and modding out by the derived group of a parabolic subgroup. And I call these Braverman-Kazhdan spaces. I think Giannis calls these pre-flag varieties, and the point is that they are torus they're torus bundles over a flag variety. So we'll see some examples of that in a moment. Another case is triples of quadratic spaces, and we'll see that later too. And this is due to myself and Liu, buying Liu at Purdue, and myself and this student Sue. there's a twisted version of triples of quadratic space, or sorry, it's not really triples. So I don't really want to get into this version. I mean, maybe I can say it's essentially you sum over a quadratic, the zero locus of a quadratic form, and you weight it by the Hecke eigenvalue, or sorry, the Whittaker coefficients of some higher rank form on GLN. And this is due to my student Pam Gu. And then recently, like the past week or so, we posted it. I developed with Youngju Che a version for Schubert cells. So, and I might say something about that at the end of the talk. All right, so now the goal for this talk let's see what we can get through, is to explain formula for fx in cases 1 and 2, and then I guess implicitly 4. Okay. So I want to say sort of, well, why would you want to find a formula for this thing? And why would you want a formula for this? So first, 2 is the first of its kind. So the nice thing about case 2 up here is that this is these triples of quadratic spaces are the first case that has been developed where you're not working with a flag variety or something that's easily related to a flag variety. So that's, I mean, this is sort of the first case in which one has sort of a case you can play with that is not of that form. And it shows different behavior, and for sort of illuminating the general picture, I think that having this experience will be important. 2, for applications, it will be necessary. So prior to the work that I'm going to talk about today, all that we knew was that the Fourier transform in, say, case 2 up here existed. And I could imagine that this sort of setting will lead to, I mean, for example, in analytic number theory, this basically provides a playground where any sort of question that you could answer using a vector space, you could try to answer in a more rich geometric setting. And I recently gave some talks on, thinking about the circle method in this context. And I think that, I mean, you certainly need to know the formula for the transformer to get these things to work. In addition, to build integral representations of higher rank L functions, and I'm currently working on this with my students, you need to have some formula in place for these things. It's not just enough to know an existence result. And finally, I think the formulas are pretty. And there will be some complications, and I don't understand all of the parameters that go into the formulae, but one thing that they make clear is that it does feel sort of viscerally like a Fourier transform. You're integrating some kernel against something, and I think that it's quite nice. Okay. Well, I also want to mention while I'm on this that I guess maybe in point 1 here, there's related work of, let me put down 2 things, some related work that I don't want to forget to mention, of William Sikorsky, who's a student of Freydun Shahidi. So he and Freydun have worked with these Fourier transforms in the case of reductive monoids, and also there's some related work of Jiang, Luo, and Kazhdan, which also essentially works with the case of a Braverman-Kazhdan space in a special case. Right, so these two pieces of work are related. I wanted to mention them. Okay, so as an example to get us going, I want to talk about an already non-trivial, but I didn't really know how to think about this when I first sort of started thinking about this subject, but it's kind of pretty to work out. So throughout this talk, I'm going to use R for an F algebra when I'm defining points of schemes or varieties. So I'll give myself a quadratic space. So a space, a quadratic, a vector space with a non-degenerate quadratic form. I'll give myself, I'll let QV be the associated quadratic form. And I want to look at the cone, which is the set of V and VR, such that QV is equal to 0. All right. Now, this is a Braverman-Kazhdan space. This has the form of an orthogonal group modulo the derived group of some parabolic subgroup. So this fits into one of the cases we dealt with above. I want to fix the form on this thing. I'll take this differential form on the cone that's normalized so that in the following way. So this allows me to integrate on the cone. So here's the theorem in a special case that I proved with Sue and Leslie. So for F that's in the Schwartz space of the cone, the Fourier transform on the cone is as follows. So maybe some of the details are not so important, but it's kind of fun to be able to say that you can write it down explicitly, at least for me. Okay, I think I need a V prime here. Yeah. All right, or P of N is congruent to N mod 2. So I'm just, P of N is just the parity. So it's either equal to 0 or 1. Okay, so maybe the details of this formula are not so important, but the thing that I'd like to highlight here is that if you had to guess, right, what the Fourier transform would be in this case, then you'd have a, I mean, what would you have? You have the space and you have a natural pairing on it that's given by the pairing that defines your quadratic form. And you'd say, okay, well, let's just take our function and integrate over the space against this pairing, and then throw in, I'm sorry, I didn't say psi is an additive character. So I'll just integrate against the pairing. That's the most naive thing you could do. And it turns out that's almost right. So the additional piece of information that you need is an additional integration along F times. And there's some weight factor that you have to incorporate, and it's incorporated in here. But it's kind of pretty because, I mean, it sort of, from some visceral level, it does look like a Fourier transform. Okay. So this formula, this is due when, oh, and I think I forgot to say here that N is my dimension of the space V. So when N is even, this is due to Kobayashi and Mono in the Archimedean case, and it's due to Gravich and Kazhdan in the non-Archimedean case. but their proof uses the properties of the minimal representation of O(n plus 2, where n is the dimension. And I won't write down what the particular form of the orthogonal group is, but it turns out that this cone is the so-called minimal representation of the bigger orthogonal group. And so their proof uses that, and therefore it doesn't generalize to the case where n is odd. Okay. So here's the other case that I'd like to mention, and this is the triples of quadratic spaces. Okay, so I give myself now 3 quadratic spaces where and let di be the dimensions of the vi, which are I want to be even and bigger than 2. I'll write down the quadratic forms as qi and let qu following. Okay. And again, in this case, I have sort of a natural pairing on my space. All right. And now I need to define a few rational functions. I mean, maybe the form of these is not so important at the moment. I mean, the thing to take away from this is just that they're, I mean, first, they're more complicated in the other case, but they're still explicit. And then V, I want to be the product from I equals 1 to 3. Okay. So now the space I want to work with is Y of R, which is the set of Y in V of R, such that the 3 quadratic forms all have the same value. Okay, and then you define some measure as before. All right, so in this case, I don't know whether the formula for the Fourier transform is valid for the entire Schwartz space. I haven't even defined what the Schwartz space is for you, but in this case, it always contains the images of Schwartz functions on the bigger vector space under restriction. Let me just look at that subspace. Okay. So here's the second theorem. So maybe I'll put it on the, okay, let's see if I can fit it. So for F in this subspace of the Schwartz space, formula looks as follows. Okay, there's a few. Okay, and I'll sort of give some interpretations of this. Details are maybe the only point at this point for the details is that you can write them down. Okay, and then times some temperature. see. Okay, so again, let's sort of have a look at this. So there's a pairing that's in play, and so you have a knee-jerk reaction is that you should take your function and integrate against the pairing. And this part of the formula sort of gives you that. You have an f of y times whatever measure you're working with. And then there's this psi of c over a y thing that's going on. What's interesting is that that's not the whole story in this case. There's another invariant that comes into play, which is this the q as opposed to just the pairing. And so you have to integrate against that. And then there's some things that are some abelian integrations that are coming out front. So, I mean, I think one of the takeaways from this is that there's still, at some level, the naive version of the pairing that's at play. But essentially what's going on is if you think about, I mean, really what you're doing, I guess, in some level is you're taking y cross y and modding out by the diagonal action of whatever reductive group is acting. And there's more invariants in this case than there are in the other case. So the formula is more complicated. But it's still something that one can write down and work with. Okay, let me just say this, that, I mean, this is maybe not so important, but this is the product. It's 1 to d over 2 minus 1 is ai di over 2 is 1. And I'm using as shorthand C1, A1, C2, C3 over 8. Okay. One immediate corollary that one can obtain out of this, which wasn't known before, is that if F is non-Archimedean, and Fy, then Fy is unitary. And you have a Plancherel type, or maybe, yeah, Plancherel formula. Okay. All right. So now I think what I will do in the remaining time is, let's see. I want to talk a little bit more about Braverman-Kazhdan spaces and say what goes on these in this case. So the thing to think about here is that this is supposed to generalize the example of the cone. So you give yourself a simply connected group. Give yourself a minimal or a maximal parabolic. Let's let M n equals P be the Levy decomposition. And then we have XP circ, it is the derived group B. This is a Braverman-Kazhdan space. And let's let XP be its affine closure. Okay. All right. So how do we construct I mean, we want to do something like what we did for the cone. And so we need, for example, we need this pairing. So how do we construct this? Well, we can choose some irreducible representation G to aught BP such that we have a Plücker embedding from XP into VP, right? So it turns out nicely that if I look at the opposite parabolic, I get the dual representation. You can identify these. And so we get a pairing. From XP cross XP op, say GA, that just sends X and X star to pairing of Plücker PX, Plücker P op, X star. Okay. So that's our pairing. And then Braverman and Kazhdan defined isometries FP P op from L2 XP F to L2 XP op. And here's the theorem that generalizes the theorem for the cone. If I take something in the Schwartz space, then the Fourier transform has the form, there's some augmentation operator and some geometric Fourier transform, where the geometric Fourier transform has the nice form that I mentioned. So it's X star. It's just the integral over XP of F of Fx psi of X star P of dx. All right. So it's exactly as we had before. We have integration against this pairing. And let's see, so what is this augmented operator? Well, the abelianization of M acts on XP op, and mu P aug is a sequence of weighted Fourier transforms. Along that action. Okay. So I think rather than tell you, I mean, maybe I'll just sort of briefly summarize what the what's relevant for this augmentation operator. So I won't write down these weighted Fourier transforms. Maybe it's not so helpful, but I mean, what's neat is that their definition involves essentially a bunch of data that's associated to the representation of the levy on the dual unipotent radical, and you essentially take the Langlands Shahidi normalizing factor for that data, and you plug in the trivial representation for your automorphic representation, and you get some piece of data, and then that gives you your augmented operator. I mean, you know, maybe it's not so illuminating for the talk. I will point out that the key observation is that you have this factorization of this form is due to it's due to Spencer Leslie, my postdoc, and in hindsight, it's the perfectly natural thing to do, but it doesn't appear at all in any of the work of Braverman and Kazhdan. I mean, so it's not at all apparent from what they did. So let's see. So yeah, so the talk is over at 8, right? Is that the, okay. Yeah, I'm trying to decide whether I should do the triple or the Schubert cell. So maybe so this is, I mean, this is new, so I want to say a little bit about what these, so the case 4 that I mentioned above are these generalized, are these Schubert cells. And implicitly what I did above gives you a formula for the Fourier transform in these cases. But I mean, this is something that I don't really understand, and we just sort of recently came up with, and maybe I'll say something about it in sort of the interest of like getting more people to think about this. So here's the setup. So we worked with this thing, which was our XP, which is P derived mod G. Okay, so here's the generalization, and the generalization is motivated by looking at Schubert cells, which are things of the form BW mod a Borel, or more generally P mod PWB. Okay, so the nice thing to think about with these sort of objects is that even if I start with a BWB, if I take its closure, it can be fixed by a larger group on the left and right. I mean, whatever fixes the left and right, this thing on the left and right is going to be a parabolic subgroup because it contains B, right? But it could be a bigger subgroup. And so you can sort of squeeze a little bit more out of the theory of Eisenstein series this way. And so here's the setup. You give yourself P inside this. You give yourself P inside P prime inside G. These are parabolic subgroups. I want P inside P prime to be maximal. And I want to give myself just Y inside G some subscheme. So I don't need it to be open or closed or whatever, but I want it to be P prime stable on the left. All right, so the thing to think about is maybe Y is equal to P prime gamma H. All right, so then I can take Y P equals P derived mod Y, which sits inside P derived mod G, and Y P star equals P star derived mod Y inside P star mod G. Okay, and so let me just say the last theorem, like I said, we just posted this like a week or so ago. The Poisson summation conjecture is true for YP, right? All right, so this is a generalization in the strict sense of the case of a Braverman-Kazhdan space, because you could always take P prime to be equal to G, right? But somehow these are almost, I mean, they're generalized Schubert cells. And as a corollary, and I won't have the time to say what this conjecture is, but the conjecture of Bump and Che on Schubert Eisenstein series is true. So Che Youngju pointed out to me that, I mean, that she and Bump had this conjecture that basically said that if you take an Eisenstein series and you restrict it to a Schubert variety, that object still has functional equations. So this came out in a paper in AJM in like 2014. And so she said, well, why can't, you know, we use some of this Braverman-Kazhdan machinery to try to address this question? And so out of that came this paper that just came up. And for me, in some sense, I don't know, in my mind, I can't figure out how to reduce this sort of setting that you can deal with out of this to the case of just Eisenstein series. I mean, in some sense, it does reduce, and that's how you prove these things. But it's not clear to me that, for example, that there aren't some new integral representations that are hiding in this slight generalization. So I just wanted to maybe end with pointing out that the theory does generalize to this case, and this is sort of something new, or at least to me, to think about. So I'll stop here.
Are there questions for Jayce? And I can't see everyone at once, so you should just unmute yourself and like speak.
In the abstract, you mentioned something about Langlands functoriality.
Yeah, okay.
So can you say some consequence?
So this is all prep, but the case that you, okay, so the case that I'm working on with my students is if you take this space Y that I mentioned earlier, okay, and I want to look at the, I want the following special case. I take GA cubed cross GA cubed, and then take the whole thing 3 times. All right, so this is a representation of GL3 cubed. Okay, the dual representation and the standard representation. Sorry, this isn't Y. This is, let me put it this way. It's my VI's are all equal to this thing, and so I have 3 copies of this. And then I look at the space that's, I form my Y out of this, which is this triple quadratic spaces space. And then I look at Y cross GA cubed, which I'm writing in this way because again, this has a natural action of GL3 cubed. And so this thing has, on the left, it has an action of my GL3 cubed. And on the right, it has an action of, let's write it as 1AX or lambda. Okay, where I want lambda 1 to be equal to lambda 2 equal to lambda 3, because these quadratic forms have all got to be the same. Okay, so I need this lambda factor it's going to act on this factor of the VI's, and it needs to act by the same scalar in each one in order to preserve the space Y. Okay, so the claim is that if you take the Schwartz space of this thing, let me call this M so I don't have to keep writing it, M cross MF. And then I let this group act on it. So I take a function here, maybe I'll work globally. And then I take a integral E of G F of maybe F of G inverse E A or DG, where phi is in some cuss form on GL3 cubed, so pi 1 tensor pi 2 tensor pi 3, where the pi i's are on GL3 AF. Then this is related to LS pi 1 tensor pi 2 tensor pi 3. So this is the triple product for GL3 cross GL3 cross GL3. Okay, and the reason I'm not talking about this yet is because there's too much that has to be developed in order to actually make sense out of this setup. For one, it's not clear that this the Fourier transform does not commute with this action, right? And two, it's not obvious, although I think I mean, it's expected. I didn't realize for a long time that this was expected, and that now I sort of see how one can go about proving this, that this preserves the Schwartz space. So, I mean, you have to develop some things about the Schwartz space to even prove that this action preserves the Schwartz space. But now I believe that this is true and that that's going to be, that will be okay. Okay, and then the final step is that when you apply the Fourier transform to get this, you're not going to land in the same space anymore because this action doesn't commute with the Fourier transform. So you have to come to grips with like, what space are you, I mean, you can think about a zeta function as some functional on some covariance of some function space. And you have to give a geometric interpretation of what you get after you do this Fourier transform. And so that's what my current work is focused on. I mean, so Spencer, there's two students that I mentioned, Pam Gu and Chun-Hsien, and Spencer and I are working on getting this all to work. So this is, and in order to get that all to work, you need to have a formula for the Fourier transform. I don't have any idea how you like think about this if you don't have a formula for the Fourier transform Fy. So I mean, so thank you for asking, because I mean, maybe this makes it more interesting other than, wow, I have this complicated formula, who cares? But, you know, that's why, I'm working on these formulae. So.
Thanks.
So Jayce, you went from the cone to triples of quadratic spaces. What happened to pairs?
Well, the cone is a pair.
That is a pair.
So if you take two quadratic forms, you take when they're equal, it's another cone.
Okay.
Right. So you're right. So so you don't move past until you, but the triple really, I mean, it does seem to be a different object.
Okay.
So that's a good question. Yeah.
What if you take tuples in general, like quadruples?
So I don't know how to do it. If I knew how to do it, then I'd be okay. Then I had proof like, I mean, then effectively, if you knew how to do it for any quadratic form, you'd be able, I mean, you could take the quadratic form to be the determinant on GL2, right? And then you'd have a Poisson summation formula for any tensor power of a GL2 automorphic representation, which would be amazing.
Phenomenal. Yeah.
Yeah. So, but the point is that what's built into this triple product thing, I mean, you actually use, I didn't have time to talk about this, but the way that you prove this is you use the triple product L function representation. You take a theta function and you plug it into Garrett's triple product, Garrett, PS, Rallis. You know, you plug it into theirs. When you think about what the integration does, it picks out the fact that your quadratic form has equal values on each. So this is a way that you can use theta functions to build new summation formulae out of old ones. And so my student Pam Gu did another case where basically instead of I mean, you think about the triple product as being like D4, you pull out the middle node if you're thinking about it in terms of Langlands-Shahidi classification. So you can say, okay, take Dn and pull out that node and then plug in two theta functions on the two like dangly legs that you cut off, right? Then, so she's got that. So she's worked that out. And so it's up online. And there are lots of other cases where one can play this game where you can try to see what kind of summation formula you can get out of this.
So in this setting, there's much done with the Plancherel theory, but like thinking from the classical theory, and you mentioned the Langlands-Shahidi setting, and to go from Plancherel measures to actual epsilon factors and the L functions, you need some multiplicity one theorems.
Right, and that's where the sphericity comes in.
Mm-hmm.
So I mean, the expectation is that when this is, you know, this idea is due to Sakellaridis, sort of the natural, I mean, based on earlier work of Jacques and his collaborators and so on, but the natural setting for expecting that multiplicity one result is when the variety is spherical.
Mhm. So it is believed that it could be possible.
Yeah, so in the case of spherical varieties, it's expected that at least the multiplicity should be finite. So and there are even cases where it's not one, and you can still make progress. So like Jacques, well, I guess Erz Lapid and Omer Offen and Brooke Feigen, I think I got the order of the names wrong, but anyway, so they worked out a case where and Jacques, they worked out a case where the multiplicity is not one, but you still have a factorization.
Okay.
So that's unitary side general linear. So even in the case where it's not local multiplicity one, it's close enough that you can proceed. That's the expectation.
Nice.
Are there other questions for Jayce? Let's thank him again.